Find the derivative of y equals f of x over g of x from first principles. We let q of x equal f of x over g of x, and so we have that if y equals q of x, then dy by dx equals the limit as h tends to 0 of q of x plus h minus q of x over h. And we recall that f dashed of x equals the limit as h tends to 0 of f of x plus h minus f of x over h, and similarly for g dashed of x. And now, because q of x equals f of x over g of x, then we have that q of x plus h equals f of x plus h over g of x plus h. And so given the definition of dy by dx, we make the following substitutions to obtain this expression, which we can rewrite as the limit as h tends to 0 of 1 over h times the numerator. And on combining the two fractions in the brackets into one with the common denominator, we obtain this expression. As it stands, this complex expression is not particularly useful, so the question is, how can we expand it? And we want to expand it in terms of f dashed of x and g dashed of x. To interpret this expression, we note that both terms in the numerator involve products, and we now apply some geometrical intuition about products. If we consider the product a times b, and we draw a rectangle whose sides are a and b, then we note that the area A of this rectangle is a times b. So if we now consider a rectangle whose sides are f of x plus h and g of x, then we see that the area of the rectangle is f of x plus h times g of x. And similarly, a rectangle whose sides are f of x and g of x plus h has area f of x times g of x plus h. Now we are interested in the quantity f of x plus h times g of x minus f of x times g of x plus h. And so we can see that this quantity corresponds to the difference of these two areas, where we subtract the rectangle on the right from the rectangle on the left. And to do so, we first superimpose the two rectangles as follows. And we note that the area shaded green corresponds to the term f of x plus h times g of x, and the term minus f of x times g of x plus h corresponds to the area shaded black and red. Now, since we are subtracting these two expressions, f of x plus h times g of x and f of x times g of x plus h, we can see that the area shaded black disappears completely, and that the whole expression, f of x plus h times g of x minus f of x times g of x plus h, corresponds to the areas shaded green and red. We now label the remaining dimensions on the diagram. The width of the red rectangle is minus delta g, which equals minus g of x plus h minus g of x. The height of the green rectangle is delta f, which is f of x plus h minus f of x. And so the area of the red and green rectangles is g of x times delta f, which is the green area, minus delta g times f of x, which is the red area. Or more precisely, it is the negative of the red area, since we are subtracting it. And we can expand those quantities in full as g of x into f of x plus h minus f of x, minus g of x plus h minus g of x, all times f of x. And so we have shown graphically that f of x plus h times g of x minus f of x times g of x plus h is equal to the expression on the right-hand side of this equation. And the new expression is useful because this quantity appears in the numerator for the expression of f dashed of x, and this quantity appears in the numerator of the expression for g dashed of x. Now recall that we are trying to compute dy by dx, which is defined by the expression shown here. We can now replace the numerator, shaded green, with the expression shaded yellow to obtain this quantity. And if we recall the definitions of f dashed of x and g dashed of x, we see that we want to combine the following quantities, shaded yellow. And so first we swap the numerators of the two fractions, and we note that we have the product of these two quantities. And now we turn the limit of the product into the product of limits, and we decompose the fraction in the second limit as follows. To obtain the limit of the difference of two fractions. And now we turn the limit of the difference into the difference of limits, like so. And we note that the quantities shaded yellow do not depend on h, so we can pull them out of the limits to give the following expression. We can now see that the expression in this box is f dashed of x, and that the expression in this box is g dashed of x, which allows us to write the whole expression as follows. And we now only have to evaluate the limit as h tends to 0 of 1 over g of x plus h. And that is straightforward. As a first step, we turn the limit of a quotient into the quotient of limits to give us the limit as h tends to 0 of 1 over the limit as h tends to 0 of g of x plus h. And the limit in the numerator is 1, since 1 does not vary with h. And the limit in the denominator is g of x, because if h tends to 0, then x plus h tends to x. So g of x plus h tends to g of x. And on applying those results, we obtain 1 over g of x times 1 over g of x into g of x times f dashed of x minus f of x times g dashed of x, which simplifies to g of x times f dashed of x minus f of x times g dashed of x all over g squared of x, where g squared of x means g of x times g of x. And so if y equals f of x over g of x, then dy by dx equals g of x times f dashed of x minus f of x times g dashed of x all over g squared of x.